Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. We're going to finish off the sun this time. We've been talking extensively about the sun in the last few lectures of this module, and we've talked about what's happening down in the core, the surface prominences, solar flares, and everything, and how energy gets transferred inside the sun from the core to the surface. But a big question remains. How do we know that fusion is truly occurring in the core of the sun? That's a really important question, and the answer involved an incredible amount of detective work that happened in the latter part of the 20th century. Neutrinos are theorized to be created in copious quantities by nuclear fusion reactions, but they're notoriously difficult to observe. It's by finally observing these that we can truly understand what's going on in the core of the sun. Incidentally, this is a great example of the way of science. We'll see that there's this back and forth process of explaining phenomena. You start with some explanatory idea, which requires some new experiment, which then gives new phenomena, which then need to be explained and tested. This is kind of check my work back and forth, is a hallmark of good science. It is also this willingness to adjust your ideas to fit reality, and not the other way around, that makes for good science. So let's go back to the equations of stellar structure to see how stars work. The core of the sun is an extraordinarily dense place. It's also extraordinarily hot and under extraordinary pressure. Outside of the core, we posit that no energy is being produced, other than through the Kelvin-Helmholtz mechanism of gravitational contraction, but that doesn't yield much energy. Combining all these equations together computationally, we conclude that the core of the sun has to be extraordinarily hot, around 15 million Kelvin. That should be hot enough, given quantum tunneling through the electrostatic barrier, that fusion reactions should occur in the core of the sun. Looking at the last equation, that dl/dr, we know that the reactions of the proton-proton chain, which is the little diagram in the lower right, we then expect the core of the luminosity to be extraordinarily large. The epsilon without a subscript is the energy created per second per particle by some material, here hydrogen fusion, in the form of gamma rays, and kinetic energy to heat the core. The epsilon sub nu is the energy generated from the form of neutrinos, which doesn't help to heat the core, but just zips out and leaves the scene. It is this luminosity due to neutrinos that we want to look for. So again, what are neutrinos? Neutrinos are fundamental, neutral, subatomic particles. They barely interact with anything. They also have a tiny but not well-known mass, and in fact are thought to be massless until only recently. They travel at very close to the speed of light, but not quite because of their tiny mass. They don't interact at all via the electromagnetic force or the strong nuclear force. They don't have an electric charge. The name itself, neutrino, means little neutral one, because they don't carry an electric charge, unlike the proton and the electron. And so they only interact with other particles through the weak nuclear force. Gravity, sure, but their masses are small, so they don't do much with that except cosmologically. Therefore, they can pass through an enormous amount of material without interacting with anything. A block of lead, 1 parsec thick, for example. They can go straight through that and not see a single atom of lead. So when neutrinos are created, therefore, at least we think they're created by fusion in the core of the sun, and every theory about nuclear fusion says they should be created, and if they are, they would simply stream out of the sun at or near the speed of light unimpeded. So what do we mean by fundamental particles? Here we see a diagram of the standard model of particle physics, together with the 6 quarks, 6 leptons, 4 force carriers, and 1 fundamental interaction. This all makes up the standard model of particle physics and comprises all of what we know about matter. These are the building blocks of all matter. Each of these 17 things is considered to be a fundamental particle, meaning they can't be broken down any further. And we see that there's 3 generations of fermions of matter. There are 3 different kinds of matter, and the most familiar are things that are constructed out of the first generation. Up and down quarks, when combined together in the right way, give either neutrons or protons, as we see in my little diagram. We also see electrons and neutrinos. So that first generation of matter is pretty much everything. Well, not pictured here are the antiparticles. So there's an anti-electron, otherwise known as a positron, and an electron antineutrino, and an up antiquark, and so on. Antiparticles have the opposite charge, parity, and time properties, but are otherwise identical to their normal matter counterparts. Our universe is dominated by normal matter, with antimatter created by various processes, and why that is, I'll leave to my upcoming lectures on cosmology. At the bottom are the leptons, and the one we're concerned about is the electron neutrino. So if a proton is converted into a neutron, or a neutron is converted into a proton, an electron antineutrino is involved via the W- boson. Typically in particle physics, a little bar over the symbol for a particle is its antiparticle. And I've demonstrated this in two ways, one with a funny cartoon I made, and the other with a standard Feynman diagram. The other generations of matter, which are charm and strange and top and bottom, quarks, have similar weak interactions via the muon and tau neutrinos and muon and tau leptons, but they don't create things like protons and neutrons. So we're going to ignore them for now, and we justified in doing that because, well, that's not really important to the process. We don't think of any kinds of things like protons and neutrons created out of these quarks. So there's not much of them in the universe. Importantly, though, there are three different kinds of neutrinos: the electron, muon, and tau neutrinos, each one corresponding to its own lepton. Over there on the right-hand side, those are the force carriers. So you've got the photon for the electromagnetic interaction, the gluon for the strong interaction, and two more bosons for the weak interaction. These things and these ideas you would encounter extensively if you went to graduate school for particle physics. Armed with the idea that there's up and down quarks, and they make protons and neutrons, and the electrons pair with the electron neutrinos, let's a little bit more about the history of how it was found, how these neutrinos were found to be coming from the sun. So there are three different kinds of radioactive decay. First is the alpha decay, in which a helium nucleus emerges from the nucleus of an atom. A helium nucleus is also called an alpha particle. Second, beta decay, in which a proton is seemingly exchanged with a neutron and an electron emerges. The electron is also called a beta particle. Third, gamma decay, in which a high-energy photon emerges. Gamma ray photons are very high-energy photons. While the alpha decay is easily understood as a chunk of a nucleus falling out, and the gamma decay is understood as energy in the form of light escaping the nucleus, the beta decay seems odd. Ostensibly, there shouldn't be any electrons in the nucleus of an atom, and that was shown to be the case in 1913 with Bohr's model of the atom, which explained Rutherford's experimental data, which refuted Thomson's plum pudding model of the atom. So, why would an electron fall out of a place where it doesn't exist? So the neutrino was postulated first by Wolfgang Pauli in 1930 to explain how beta decay could conserve energy, momentum, and angular momentum, and Pauli hypothesized an undetected particle that was emitted from the nucleus together with the electron, or the beta particle, in the process of a beta decay. He called it a neutron. In 1932, James Chadwick discovered a much more massive neutral nuclear particle, and he named it a neutron also. So for a short while, we had two different kinds of particles with the same name, and the word neutrino was first used publicly by Enrico Fermi during conferences in 1932 and 33. And during his second conference, Pauli also used the name. And the name, the Italian equivalent of little neutral one, was coined by Edoardo Amaldi during a conversation he had with Fermi in the 1932 conference. And they were trying to distinguish between this light little neutral particle and Chadwick's heavy neutron. Pauli believed the neutrino was completely without mass. This idea of a massless neutrino was not overthrown until the solution of the solar neutrino problem, which showed that they had very, very tiny masses. In 1934, Fermi came up with a theory of beta decay. Chadwick's large neutral particle could decay into a proton, electron, and a smaller neutral particle, which we now call an electron antineutrino, via the reaction shown in the middle. Fermi's work unified Pauli's neutrino with Paul Dirac's positron and Werner Heisenberg's neutron-proton models to give a solid basis for future experimental work. And that was their goal. It's like, well, there must be something here, so let's figure out a way to make it observable. In 1936, the second lepton, the muon, was discovered by Carl Anderson and Seth Nettermeyer at Caltech while they were studying cosmic radiation. And they found it because due to the fact that muon trajectories in a magnetic field were really different from electrons and other known particles. And it was supposed, because of the trajectory change, that their mass was much greater than that of the electrons, but smaller than the protons, which is about 200 times that of the electron. Well, this new lepton led Isidore Isaac Rabi to say, who ordered that? And so that particular thing has made its way through all of physics. The tau lepton wouldn't be discovered until the 1970s by Martin Lewis Pearl using the Stanford Linear Accelerator and Lawrence Berkeley National Lab equipment when they found some odd events involving the positron-electron annihilation. They had to posit a new lepton and its antilepton in order to take into account the observed particle reactions. But let's take it back a bit. Initially, Fermi, Pauli, and others thought neutrinos were massless and undetectable. And in 1941, the muon was shown to decay into one single electron, and since nothing else could be seen, the physicists suspected that a new kind of radioactive decay that yielded a new neutrino had been found. A big mind in early particle physics, Bruno Pontecorvo, worked on the idea of neutrinos' detectability. In 1945, Pontecorvo noted that a neutrino striking a chlorine nucleus could transform it into an unstable argon-37 that emits an electron via beta decay with a 34-day half-life. This allowed for the idea of the neutrino's direct detection. Next, Pontecorvo suggested in 1957 that neutrinos might oscillate, change from one type to another because of their difference in mass, and we'll see why shortly. In 1959, Pontecorvo further showed that neutrinos that were produced in decays of particles from an accelerator could be observed with really large detectors and proposed an experiment to find out if electrons and muon neutrinos differ from each other. The eventual discovery of the neutrino oscillations by the Super-Kamiokande experiment in Japan was a triumph for Pontecorvo's ideas, but it came about a decade after he died. So let's see how neutrinos are produced. Remember in a previous lecture, I talked about the proton-proton chain. Soon after the muon was discovered, Hans Bethe, in 1939, published his paper that completed the details by which stars fuse hydrogen into helium. And this is the proton-proton chain. His big breakthrough was to examine the step that created deuterium and making it into a series of other steps after that. The first and most important step was the formation of deuterium. When deuterium is formed, an inverse beta decay happens. A proton's quarks interact with the weak nuclear force, changing an up quark to a down quark. In so doing, a neutron, an anti-electron, and an electron neutrino are formed. The anti-electron in that beta plus is that beta plus that's scooting off, which immediately hits an electron, annihilates, and creates two gamma ray photons. The neutrino is that little V kind of thing. The neutrino, as per Bethe, doesn't notice any of the high density of the sun's core and simply departs at nearly the speed of light. So if the proton-proton chain is happening, then neutrinos should be streaming out a lot. How much? A lot. To account for the luminosity that we see of the sun, this reaction has to happen 10 to the 38th times each second. This is an enormous amount. Wouldn't we run out of protons at that rate? From a previous lecture, we learned that about a third of the mass of the sun is in its core. Making the lightly bad assumption that it's made up all of protons, then we get that there's about 10 to the 56th protons in the core. Since if you take 10 to the 56th and divide it by 10 to the 38th, you get about 10 to the 18th. And that gives us about the guess, a pretty good guess, as to the lifetime of the proton-proton chain in the sun. And since 10 to the 18th seconds is about 10 billion years, well, That's a lot of stuff down there in the core of the sun. The sun is really, really big. So if 2 times 10 to the 38th neutrinos escape from the sun every second, and if we think of them as spread out evenly, then they come out in every direction randomly, then they should be distributed evenly over the surface of a sphere centered on the sun. If they distribute over the sphere, then how many neutrinos go through each square centimeter at a distance of 1 astronomical unit? We expect to see over 60 billion neutrinos pass through every square centimeter on the surface of the Earth. That means if you hold your thumbnail towards the sun, every second, 60 billion neutrinos go through your thumbnail. Each second. That's pretty crazy. So imagine there's a number of skeptics that say, really, 60 billion neutrinos coming from the sun through your thumbnail every second? And that's for every thumbnail positioned at 1 astronomical unit in any direction from the sun? Okay, that's a lot. But where does that number actually come from? Well, remember we used the equations of stellar structure along with the reaction probability of the proton-proton chain, and you plug that all into computer simulations. These are really well known and really well understood physics and really well understood computer simulations, and they take as their input the bulk properties of the sun, like its total mass, observed luminosity, and surface temperature. We take all these surface bulk conditions and ask what would produce those outputs down in the core. And from my video on energy transport and stellar structure, we can run those simulations from the surface to the core and the core to the surface and back and forth towards each other until you get a good model that converges for both directions. And you get that convergence, we use the fact that the sun is really old and in thermal and dynamic equilibrium in the broadest senses. Basically, whatever energy is leaking out from the surface has to be replenished at the center. Now, it's hard to detect these neutrinos, but they are part of the energy budget that's coming out of the core and a required output of the proton-proton chain. And so because of this process, you can make a very robust set of predictions, and specifically about what the energies of the neutrinos are, not just that there are neutrinos, but how much energy that they have as they come out and that they take with them. We can then arm ourselves with this prediction of how many neutrinos from the postulate that nuclear fusion powers the sun and go look for them. So the hunt was on, but the detection of neutrinos is very difficult. Researchers understood that they needed to use a huge amount of some very heavy materials, such as gallium or heavy water, to provide a uniform material that's somewhat susceptible to interacting with neutrinos. And so this material would be placed deep underground because cosmic rays can cause interactions in the material, just like the neutrinos. And so the Earth itself has to be used as a shield. Cosmic rays are high-energy particles that stream from galactic space and impact the Earth's atmosphere. They create showers of high-energy particles in so doing that then decay into neutrinos. This is a source of noise that needs to be removed by going deep underground. Now, it's not a surprise that experiments have detected them, and it's well understood today that they have. So I know this is giving away the story at the beginning, but just getting neutrinos that come directionally from the sun and have the calculated energies gives us extreme confidence that fusion is happening in the sun's core. So let's look at some of the experiments that went on this epic hunt. The first really important neutrino detector was the Homestake Mine neutrino detector. It was designed by Raymond Davis, and John Bacall provided the theoretical background. And it was founded basically on Pontecorvo's reaction that he had discovered in 1945. This was Bruno's big idea for a big experiment. And Davis and Bacall ran this from 1970 through 1994. It was located in an old gold mine in Lead, South Dakota, about a mile underground, and that shielded it from the cosmic rays. Davis's experiment filled this 100,000-gallon tank with dry cleaning fluid, which contained the chlorine needed. Some of the chlorine in the solution would extremely rarely react with an incoming neutrino to form argon-37. Now, this reaction has a threshold energy of about 800 kiloelectron volts, so the Homestake Mine detector was sensitive only to solar electron neutrinos from the proton-proton chain and couldn't detect any other neutrino flavors. To measure the reactions, every 3 months, the carrier argon, which is argon-36, and any additional argon-37 that was produced during the run were removed from the detector by bubbling it through with some helium gas. So they had to pump the whole thing out. The argon was then purified with gas chromatography and pumped into a proportional counter. They then counted all the individual atoms of argon-36 and argon-37, those two isotopes. This then counted the total number of neutrinos that had interacted with the chlorine. This is an incredible undertaking, but what they found was very weird. For 22 years of running the experiment, Davis's team always only found 1/3 of the neutrinos that were expected from Bacall's predictions using the standard solar models. Where were the other 2/3 of the expected neutrinos? So therefore, the theoretical background, well, Bacall thought it was complete, and the first response from the scientific community was either that Bacall or Davis had made some sort of epic mistake. Bacall's calculations, he checked them repeatedly, have other people check them, and no errors were found. Davis scrutinized and went over his experiment, and he insisted there was nothing wrong with it. And Bacall was stunned by this, and he went round and round trying to figure out what the heck was the issue. It was this discrepancy that created the solar neutrino problem and spurred other experiments along to solve it. And since this isn't a murder mystery, Davis was eventually vindicated and co-awarded the Nobel Prize in 2002. During the time that the Homestake Mine was making its detection runs, physicists Stanislav Mikheyev, Alexei Smirnov, and Lincoln Wolfenstein developed the idea that neutrinos could transform into each other much more easily in the presence of matter. In this way, as they traveled out the sun's bulk, they would transform from one flavor into another, and this provided a possible avenue to solve the discrepancy found by the Homestake experiment. And specifically, the dates were in 1978 and 79. Lincoln Wolfenstein found that the oscillation parameters of neutrinos are changed while in the presence of matter. And in 1985, the Soviet physicists Mikheyev and Smirnov predicted that a slowly decreasing gradient in the density of matter would resonantly enhance this mixing that Wolfenstein discovered. And Pontecorvo looked on since he posited decades before that this might be the case. And he passed away in 1993, but his contributions are recognized by the community and critical insights and advancements. Now, the exact mechanism for the MSW effect, named after Mikheyev, Smirnov, and Wolfenstein, has to do with the weak nuclear force and its very short range of effect, and the density of electrons. The higher the density of electrons, the greater the effect. Remember that neutrinos don't interact via electromagnetism or the strong nuclear force, only the weak nuclear force and gravity. This MSW effect shows that there's a small chance that the neutrino does make the change, but it needs to pass through a lot of matter and specifically a lot of electrons to do so. But the sun's got that covered. The huge mass of the sun provides an ample opportunity for the neutrinos to make the change from one flavor to another. Yep, that's what they're called, flavors. You can thank UC Berkeley for that. And the MSW effect has been confirmed for cosmic rays passing through the Earth, and the effect is a real one. Further, supernova 1987A's neutrino counts in the various experiments across the globe could be understood only if the MSW effect was taken into account, as the neutrinos pass through the Earth at differing depths. So notice it was really only completed in 1985, and 2 years later, here's the supernova that could test this idea. That's amazing. Now, to understand how the problem was solved, we need to know what an experiment might look like with a different kind of detector. If you've ever seen photos of a nuclear reactor, like this one, you might notice a blue glow surrounding the core. This phenomenon is called Cherenkov radiation, and it's a shock wave of light. Cherenkov radiation was first discovered in 1934 by the physicist Pavel Cherenkov from Russia. From Russia. Now, Cherenkov radiation happens when electrically charged particles, like electrons, travel faster than the speed of light in a clear medium such as water. And when an electron or neutron travels through the water at this high speed, it interacts with the atoms of the water molecules to give off light. This all happens because the speed of light in water is about 75% of the speed of light in a vacuum, which allows for the possibility of particles emitted from nuclear fuel to move faster than the speed of light as light goes in water. And they actually do. As this charged particles disrupt the water molecules in their path, photons are released and it creates a visible shock wave of blue-violet light. This is similar to a sonic boom when objects move faster than the speed of sound. And in fact, brain cancer patients have seen these flashes of bright blue light in their eyes when receiving radiation treatments. That too is Cherenkov radiation. So here's how it works. When a neutrino enters a huge tank of pure heavy water, the neutrino might hit an electron in some atom, and that causes a recoil action. It'll be like a billiard ball that's going almost the speed of light. When it whacks the electron would then be ionized from the atom and speed away with a huge amount of energy. Now, if this speeding electron is moving inside a medium like water at faster than the speed of light in water, you get the Cherenkov radiation. It's just like as in sonic booms and bow shocks, the angle of the shock cone is directly related to the velocity of the disruption. So the radiation makes a cone shape, but there's a minimum energy to make this kind of radiation. And the Cherenkov angle is 0, meaning at this threshold velocity, meaning it's a dot or a point. The angle of the cone takes a maximum as the particle speed approaches the speed of light in a vacuum, in excess of the speed of light in the water. Hence, the observed angles of incidence can be used to compute the direction, speed, and energy of a Cherenkov radiation-producing charge. Another way to make the radiation is for the neutrino to cause a nuclear reaction, which transforms a nucleon into other particles, and specifically, an electron bursts out of the nucleus at high speeds to create the light. Let's look at one of the experiments that did this. The Kamiokande experiment was started in 1983, and it was a cylindrical tank, about 3,000 tons of pure water, and had 1,000 photomultiplier tubes attached to the inner surface of this. And the height of the detector was about 16 meters, and it was about 15 meters in diameter. And this was hunting for, specifically it was created to hunt for proton decay, and that was the physics goal of it. The upgrade to this project was the Super-Kamiokande, and it started operation in 1996. Super-Kamiokande neutrino detector was also a big stainless steel tank like this, but it was almost 40 meters in diameter and 40 meters tall, and was filled with 50,000 tons of ultra-pure water. And there were about 13,000 photomultiplier tubes installed all along the tank walls. So the detector is, of course, located a kilometer underground in a mine called the Sudbury mine near the city of Hida in Japan. And what you see here pictured is the interior of the Super-Kamiokande detector. And so all of those balls on the wall, those are the photomultiplier tubes surrounded by a glass ball. And of course, you got to go in and do maintenance, and that's why the guys are in there in a raft. This experiment could tell the energy differences between the low-energy neutrinos that were coming from the sun and the high-energy ones that were coming from cosmic rays that hit the Earth's atmosphere. And they were fewer high-energy neutrinos towards the center of the Earth. And that means those neutrinos were being transformed as they passed through the Earth. And so the MSW effect was real for these cosmic ray neutrinos. So not only did the Kamiokande experiment confirm this neutrino problem and the fact that the light, because of the Cherenkov light made a cone, they showed the direction of the origin. And this proved that neutrinos were indeed coming from the sun. using the timing and charge information recorded by each photomultiplier tube, and where the point was the interaction vertex, meaning that in this image we see here, this ring of detection and the flavor of the incoming neutrino could be determined. From the sharpness of the edge of the ring, the type of particle can be inferred. The multiple scattering events of electrons, there's a bunch of them and they're large, so electromagnetic showers produce fuzzy rings. But highly relativistic muons, in contrast, they travel almost straight through the detector and produce rings with very sharp edges. So that's how they can detect the difference between a muon neutrino and an electron neutrino. So they announced the first evidence of neutrino oscillation in 1998, and this was the first experimental observation supporting the theory that neutrinos had non-zero masses, and a possibility that people had been speculating about for years. But the design of the experiment was to detect proton decays and not explicitly these solar neutrinos, so its results were really compelling, but they weren't the final word. Just for amusement, it's such an amazing view. Here's another view of the interior of the Super-Kamiokande detector. Look at this. Look at how pure that water is, because this is a cylinder, not a sphere. So we're looking at some amazing, amazing work that's going on through this thing. And I can't even tell where the bottom of the pool, the tank is, and where the walls are. It's almost impossible to tell from this image. Also, I'm sure that they have to be extremely careful about what tools they take in there, because you drop a hammer, you break that thing, and then you got to drain all the glass, all the water out, and pick out all the glass and repair something. So I'm sure that you have to be a very special sort of someone to be in that raft going around doing the cleaning and inspection. The final critical experiment, the Sudbury Neutrino Observatory, used heavy water, where one of the atoms of the hydrogen is deuterium, and that was used to detect all three flavors of neutrino. This detector was turned on in May of 1999, and it ran until the end of 2006. It was run in two modes of detection, one for electron neutrinos and the second for all three types of neutrinos. And the first scientific results were published in summer of 2001. And this presented the first clear evidence that neutrinos oscillate. That means they transmute from one to the other as they travel from the sun. The oscillation also then implies that neutrinos have non-zero masses. And those non-zero masses are listed in the little boxes above because mass is equal, well, remember from Einstein's equation, E equals mc squared. The energy is either in the form of mega electron volts or electron volts. And if you divide it by c squared, you get a mass. So this is fairly typical for particle physics to quote masses in this way, like electron volts per c squared or mega electron volts per c squared. And notice these are upper limits. So the lower limit, or the exact measurement of the mass of the neutrinos, they know an upper limit, but they don't know a lower limit. They don't know how tiny it could be, but they know it has to be less than this, and it has to be some mass. So the total flux of all the neutrinos that were measured by the Sudbury Neutrino Observatory agreed with all the theoretical predictions. And though the Super-Kamiokande had beat the SNO to the publication, and they published some of their oscillation evidence in 1998, the Super-Kamiokande results were not as conclusive and did not specifically deal with solar neutrinos. The Sudbury Neutrino Observatory were the first to directly measure the oscillations for all three types because it could be run in those two modes. One mode just looking only for the electron neutrino and one looking for all three. So this was incredibly important because it supported the evidence for the standard solar model. As neutrinos streamed out of the sun, this neutrino observatory was able to see that yes, they were coming from the sun, and they were that they had the right energies for each of the different kinds of neutrinos. So the validation that nuclear fusion happens in the sun and the standard solar model is a real thing. This was such an important development that in 2015, the Nobel Prize for Physics was awarded to Arthur McDonald of the Sudbury Neutrino Observatory and Takaki Kajita of Tokyo for the discovery of these oscillations. And these teams showed that the neutrinos do indeed transform and that all the neutrinos are there when the MSW effect is taken into account. And this solves the riddle, the solar neutrino problem that was posed by the Homestake Mine. So, neutrinos have been discovered. And this amazing back and forth between theoretical ideas and experiments that were devised to test those hypotheses is a testament of the robustness of the scientific process. And even the big scare that Davis and Bacall had with their experiment was critical for this advancement, since they put out their results to encourage others to either help them or find where they went wrong. In the end, they didn't do anything wrong, but they weren't able to take into account the MSW effect until it had been devised. And in fact, the Homestake Mine couldn't detect the other two neutrinos anyway. Hans Bethe's concept about the proton-proton chain was written quite soon after the discovery of the electron neutrino, but he couldn't have included the neutrino oscillation because the idea hadn't been developed yet. It is this adaptation to the shifting understanding and advancement of knowledge that is the hallmark of great science. It wasn't that, oh, there's 2/3 of the neutrinos. We know there should be there, but we just might have something wrong with our experiment. Maybe there's something wrong with our calculations. What did we do wrong? And so other people came along and did other tests to see if that could be true. And they were vindicated. The neutrino observatories fundamentally directly measured the processes that were happening in the center of the sun. And the Homestake Mine was measuring them, but they just weren't sensitive to these other energies, these other higher energy neutrinos. That's amazing. So now that we know that nuclear fusion actually happens in the sun, and therefore in other stars, what happens when the star, or the sun, runs out of hydrogen in the core to fuse? And that's a really good question, and we'll get into that next time. I do hope you enjoyed this video. Please subscribe and like this video, and I wanted to say a big thanks to my Patreon supporters who, without their help, it would be very difficult. So thank you all to my Patreon supporters, and we'll see you next time.